Morning, everyone. Is it morning? Yes, it's morning. All right. Excellent. Bale, I got your email. I haven't looked at it yet, but I saw you sent me something. You must have spent some time on it because I thought at least your tagline said you played around with Desmos too. So,
Oh, I think I solved it.
Outstanding. I'll have a look at that. Okay. We are going to look at something cool today called the product rule. And maybe even a little bit in tomorrow. So, intro. I don't know if you've kind of noticed this, but just as a for instance, if you had some equation like y equals 5x squared, really kind of that fact that it was multiplied by 5 just kind of came along for the ride, I guess you could say. It's almost like you sort of think of it as, oh yeah, there's a 5 there, but then there's an x squared. And so when it comes time to take its derivative, again, that's the quickest symbol for a derivative, but we're going to make use of the other one today. So I'm going to rewrite that right now, just real quick. dy dx is in a sense a better way to say it, only because it's like the change of y over the change of x. You can see the slope written in that statement right there, but it takes more time. And so I kind of like y prime better myself because I'm lazier. But the point is when you take the derivative, you just kind of look at that x squared and say, oh yeah, it's 2x. And then really the 5 just came along for the ride. I mean, what we noticed in class, you didn't necessarily write it that way. You just said, hey, this 2 right here gets multiplied by the 5 and it turns into a 10, and then x just gets reduced by 1. But what I want you to notice, I guess, is just that constants just kind of come along for the ride. You sort of don't have to worry about them. You can't erase them, but they're just kind of there. And if there's any other constants that result from this, like the 2 did here, it just gets multiplied and so forth. So it just kind of came along for the ride. And then the second thing that we noticed is, if you had some problem like y equals x cubed plus x squared, just to keep it simple, derivatives kind of liked plus signs. In other words, did we care that those two things were added? We sort of didn't. In other words, it's kind of like the plus signs, as I said, that calculus derivatives love plus signs. So you just look at the x cubed and take care of that. And you say, oh, the power rule says that'd be 3x squared. And then you throw a plus sign. It's like, I haven't even looked at the x squared yet. I don't care that it's sitting there. And now I look at it and go, oh yeah, the derivative of x squared is 2x. And so I can do them separately. Does that make sense? So constants come along for the ride, and plus and minus signs are awesome because you can do them separately. But ultimately, kind of today's discussion is kind of like this. What about like, y equals x to the 5th times x to the 2nd? Now, in this case, you could actually multiply that out. So we'll talk about it. But really the question is, does that work the same? In other words, x to the fifth, let's see, I can do that. That's 5x to the fourth. And then, oh yeah, there's a multiplication sign there. And then what's the derivative of x squared? Oh, that's 2 times x. And so, the question is, and this is an important question mark, is that true? Like, does that work? Do multiplication signs come along for the ride? Now I want to give you a second to think about that, because you can actually answer that question yourself.
When you multiply units with exponents, don't they add together?
Yeah.
So wouldn't this be incorrect per se?
Yeah.
Because you could just add the exponents together?
Yeah, like you're not stuck with the multiplication sign here, right? Does that make sense? So you could get rid of it. In other words, you could look at this problem and say that's just really x to the seventh, and hence y prime would be 7x to the sixth, right? So that's definitely the right answer to this question. But down here, it seems to say that the answer would be 10x to the fifth, right? So apparently the answer to this, if you will, is unfortunately a resounding no. Because this one is a yes, and that's not the same answer, right? So apparently that isn't quite that simple, which is kind of a bummer. Wouldn't you agree? It's like, now, in this case, we're able to get rid of the multiplication sign, but later on in this class, it'll be things like, y equals x times the sine of x. Like you're stuck with junk times junk there. Does that make sense? You're not going to get rid of the multiplication sign. And apparently what we just learned is that the derivative of that is not just the derivative of x times the derivative of sine. Now, you don't know what the derivative of sine is yet. We haven't got there. So we got a lot of stuff to talk about. We don't know what the derivative of natural log is. We don't know sine. We don't know tangent. We don't know 2 to the x power. There's a lot of derivatives we don't know yet. We've got some work to do. But apparently this is not simple. It's kind of the idea. Or today, like you can answer this right now. Apparently if f of x was equal to x to the fourth times e to the x, you do know the derivative of e to the x. That's the one weird thing you know the derivative of now beyond just power equations. Apparently f prime of x then is not equal to just 4x to the third times, in other words, the derivative of x to the fourth times the derivative of e to the x, which is e to the x. Apparently that's not the answer. And again, in this case, you can't get rid of that multiplication sign. So, what are we going to do with this mess? Do you see what I'm saying? What are we going to do if we have junk times junk? Apparently the derivative to that is a little more complicated. The derivative, again, just as kind of a highlight, the derivative of junk plus junk, yeah, ignore the plus sign and do them separately. If it's junk times junk, though, not so good. And thus, there's a whole chapter here called the product rule. I mean, if that had worked, we wouldn't have a rule called the product rule, right? It's like somehow we got to figure out how to do this, and so it's a little worse. And so, geez, what am I going to do? And just to give you a little historical context, I'm just sort of making up historical fiction here, but as soon as a mathematician, Leibniz, or why can I never remember the other guy's name? He's more famous. I'll think of it in a minute. As soon as they decide that this is Newton, as soon as this is like a worth doing, like, hey, I'm going to use this to find the rate of change or how fast that boat is traveling or whatever motivated their reason to want to take a derivative, a slope, or rate of change in the first place. It must have been interesting when they said, okay, cool, let's figure out how to do this with other things. It must have been interesting when they got to the conundrum we just got to, which is, well, what do we do now? Like, this isn't apparently working. And so how are we going to get out of this mess? And, I wonder how long it took them to figure it out. I wonder, back in that day, it was people writing letters back and forth to each other, like the two nerds on the earth that thought this was cool would write letters to each other, and it would go on a ship and take like 10 years to get there. And then, then they would respond back, and here's what I tried. And, it's like, I wonder how long that went on. I mean, that's just kind of an interesting part of history that was lost here. Or perhaps, as in the case of calculus, there were two people, Leibniz and Newton, who were working on this independently and they didn't know it. So it wasn't like they emailed each other and said, hey, what progress are you making? They were kind of inventing it somewhat simultaneously. And, I wonder when they ran across this problem. And so can you just see that this is what mathematicians do? They come up with a kind of a process that's kind of cool and worth something. And then they just say, well, does it work in this situation? Do you understand that the answer to this question could be it's impossible? They would not have known whether there was a way to do this or not. One of the things that kind of makes learning just so boring and makes you hate learning when you grew up, when you were little and you loved it, is because every path you follow is some, I don't know, dude like me who just runs you down the path like there's no other choices here. Is this possible? I mean, it takes the fun out of it. Given that I'm going to answer this 15 minutes from now, it would be a way better way to learn math if you actually wanted to learn math and not just get, a stamp on you that says calculus is over with, which again, I'm sympathetic to if you want to be a veterinarian, like who needs calculus to fix dogs? But it's like, this takes the fun out of it. The fun of it is being presented with a challenge like I presented you yesterday and just leaving you to think about it. Now you're lucky because the challenge I presented to you yesterday, I have already done and I know that you can do it. But in the real world, when you ask an interesting question, that answer could be an awful long time in coming, and it may never come. You may turn your attention to, now that you've tried for 3 years to figure out how to take the derivative of junk times junk, you might turn your attention to somehow proving that it can't be done so that then you can quit. I proved it's impossible, therefore now I can quit, instead of just going insane trying to figure it out. So just think about that, because what we do for education is not the way the stuff was invented. It was not as fun. It's not as fun for us as it was for them, because this is a script. Have you been on one of those, like a scripted tour where you walk down a hall? I got to go to George Washington's house, one of those ones that I was out there on the East Coast, and it was like you got to walk through his house, but there were tour guides telling you to move, and there was a rope, and so you just followed a course, and you couldn't, when you got into the room, like you couldn't go past the rope to like touch the bed or look out the window. It's like you just had to stand there and move along with everybody, and it's like, what a boring tour. I want to climb on the roof and like crawl into the cellar, and nope, can't do that. It's like a guided tour. Well, it wasn't as cool as it would have been. So I only say that just to say, there's nothing wrong with what we do. If you're going to do this in a group and get the tour over with, you got to kind of do it that way. But it does take a bunch of the fun out of it. And so, it's not as simple as we might like. It is not mathematicians making this more complicated for us. But again, the conundrum ultimately has been solved. Like, this has been figured out. I ran across this book called Calculus Made Easy, which is, you've heard of those, Macintosh for Dummies books or C++ for Dummies. It's kind of a cool book series because it's kind of like teach me something, but just speak English and cut the nonsense out. And there's a book called Calculus for Dummies too. And but this book that I'm talking about it's called Calculus Made Easy, and it was actually written in the 1800s, and it was in a sense the first Calculus for Dummies book. And that kind of stuff appeals to me. Like explain it to me in a way that I can completely make sense of. Don't try to use simple language in everyday life and use toothpicks and toothbrushes and dogs and stuff to explain it if you can. And anyway, this particular book, I'm sort of indebted to him for what I consider to be a cool way to create this. And I could just write the product rule down and then say, isn't that cool? Now let's go use it. But I want to build it for you, and not so much build it for you, but help you understand how you could make this for yourself, or how the smart people who forged the trail for us here the first time, like, found a way to answer this question. Because right now I'd be willing to bet, if I've at least made this interesting enough to you to wonder about, you might be thinking, I don't even know what to try. Like, what would I try? What if I don't separate these? If I leave back here, if I leave these separately, leave them separate, like what would I do? I do know the derivative of x to the fifth is 5x to the fourth, and I do know the derivative of x squared is 2x. But like, how would I somehow mix those together in such a way as to actually get the correct answer, which apparently is 7x to the sixth? And part of me wants to say things like, well, make conjectures like, hey, 5 plus 2 is 7. Maybe you're supposed to add those two. But then I see x to the fourth and x to the first, and I think, how are you supposed to get an x to the sixth out of an x to the fourth and an x to the first? And so, it's like, I don't know. And this is pretty hard, right? And again, I'm taking the fun out of this by telling you too soon. But what I'm going to show you now is Sylvanus P. Thompson's calculus for dummies technique in the 1800s as to how he figured it out. So let's not show you the product rule. Let's not prove the product rule. Let's build it. This is my favorite way to think about math. Let's build the product rule. Let's make it for ourselves. It's a tool. It's something you can make for yourself too. Like, it's not genius. Now, that whoever thought of a way out of this mess, I'd say was genius. But once you see this good idea, like, you should be able to build it for yourself later too. Or maybe some of you are a future teacher, or maybe it's 2 years from now and when you forgot it, or you want to show somebody where it comes from. Anyway, stop rambling. Okay. Y equals U times V. So there is junk times junk. And so I'm not thinking of U and V so much as like their own new letters. I'm thinking of them as, well, functions of X. In other words, we're going to sort of pretend that this is something like X to the fourth, and this is something like E to the X. And so, like we did just a minute ago, in other words, those are functions of X. I'll abbreviate it, functions of X. So it's junk times junk. Now, this explanation gets back to what a derivative really is. So let's just think about that for a second, because I'm always interested that you get conceptual understanding. So I'm sitting right here at the point XY, like some spot on this curve. I'm sitting right there, and I'm not just interested in, where am I right now? Oh, I'm at the 0.36, but I'm interested in how is it changing? How is things changing? I'm interested in the slope. That's what slope means. It's not so much a drawing of a tangent line. It's just, hey, I'm sitting here at the 0.35. I wonder if I change X a little bit, make X a little bit bigger, I wonder what will happen to Y, right? Isn't that what a derivative is conceptually? I'm just wondering about how things are changing. And so in order to get to this next point up here, which is what I'm curious about, what I'm really going to do is take X and add a little bit of X to it. Isn't that what I'm doing? Is like we said, if X was 3, then we went to the X is 3.01. That was kind of like our H, if you will, in the definition of a derivative. I added a little bit to that. And then as a result of that, then, Y gets a little bit bigger too. And so my new X coordinate is now just a hair bigger than it used to be. And then also, isn't your Y coordinate also a hair bigger than it used to be? I mean, this is what calculus really is changing things. How does changing things work? And so if I say I'm up here looking at this equation, which is function times function, junk times junk, then really a derivative is saying, okay, well then let's let Y grow a little bit, and let's let U grow a little bit. Oops, not Y. And I'm not going to ask you to do this on a test. I could, lots of teachers would, but I just want to help you build it, help you understand that it makes sense where this comes from. And then let's let V get a little bit bigger too, a little bit of V. So it's like you take V and add a little bit to it, take U and add a little bit to it, take Y and add a little bit to it. This is kind of what a derivative is. Now remember though, I am multiplying these two statements together, so it's kind of important to go throw those parentheses in there, right? Because I'm multiplying them. So in a sense, this is what a derivative is really telling you. But of course, what we're really after with a derivative is actually kind of dy dx, or change of y over change of x. I need dy dx, and I'm looking at this thinking, I don't see that anywhere. Well, I see a dy, but there's no x's. Well, there kind of is, because u is a function of x. I just haven't picked what it is yet. So let's wade into this a little bit. Well, at least I see something to do now, which is at least I could multiply this out. Like I could say, okay, fine, y plus dy on the left side. The right side, if I use the distributive property, would be u times v. In other words, the two functions that I haven't named yet multiplied together. And then it would be u times dv. And then v times du. or du times v. I think I'm going to write it in a different order. I'm going to stick with the order I had it in. Du times v, and then finally du times dv. And of course, your first thought should be, where could this possibly be going? You know, like, what good is this doing? This is just a giant disaster. But now there's two things I can do to this that are actually kind of cool. One of them is, didn't we say back here in the beginning that y was equal to u times v? So what if I took this u times v and replaced it with y? Why is that kind of cool?
Now we can subtract out the y on the other side.
Yeah, now I can kind of simplify this a little bit, and that's not obvious. In a sense, Vail read my mind. The fact that there's a y on both sides means I could actually subtract that y off of both sides, and so that's kind of cool. So now my ugly disaster got a little bit easier. And then secondly, I want you to think about this guy over here. What's the meaning of that? Like, what is that worth? Well, remember on the graph, it's back up here. Ultimately, dx is tiny, right? And we're even going to let it be equal to 0 ultimately with calculus. But remember, what the key to that was, we can't do it too soon. Do you notice if we did it right now, down here in this blue expression that I have, if we let dx and dy be 0, if we let du and dv be 0, we'd have 0 equals 0. And it's still broken. Like, we can't let that happen too soon. However, dx and dy and du and dv are tiny. So this is actually tiny times tiny. What kind of a number is that going to be then?
Really tiny.
Really tiny. Like super tiny. I don't know what to call it. It's really tiny. In other words, this thing is on its way to 0. I mean, all of them are on their way to 0, but this one is really on its way to 0. And so this is a bit of hand waving, because it's kind of like, can I just call that 0 now? Well, it is going to go away. And if, as I said, if we do this too soon, everything goes away. But that is going to go away. You can appreciate that. And now there's just sort of one last step, and I'm actually done. If I now took both sides and divided by dx, and the reason I did that is because, remember, what we're looking for is dy divided by dx. So I have a dy, but I don't have a dx. But if I divided both sides by dx, I'd have dy divided by dx. So wouldn't that be dy divided by dx equals u dv divided by dx, because that's still there, and then this is still there, plus du times v, looks like a u, divided by dx. And now we're here. We have the product rule, the recipe for the derivative of a product, I guess you could say, a little abbreviation. What is it? Well, dy dx equals dy dx, or y prime, like that's another way to say that, right? Just derivative, equals u times dv dx. And isn't, you know, in terms of writing it down simply, isn't dv dx just kind of v prime? And isn't du dx kind of just v prime? I'm sorry, u prime. So in other words, really what this is equal to is u times v prime plus u prime times v. That apparently is the recipe. That's kind of surprising. That's kind of weird. Well, let's try this out then. A second ago, we tried to take the derivative of x to the 5th times x to the 2nd, and we knew the derivative to that was supposed to be 7x to the 6th, since that's really x to the 7th. But let's try out this new recipe we just found that sort of tells us what to do. So this is kind of like my u term, and this is my v term. So apparently y prime is equal to, well, u left alone. So okay, x to the fifth, I left it alone, times the derivative of v. So v is x squared, so its derivative is 2 times x. And then there's a plus sign. Okay, it's always a plus sign. That's cool. And then it's the derivative of u. U is x to the fifth, so that'd be 5x to the fourth. And then times v left alone, times x squared. What is that? Let's see. X to the fifth times x is x to the sixth. So that'd be 2x to the sixth. And then x to the fourth times x to the second is also x to the sixth. And so, hey, cool, they're the same, they're common terms. And so two apples plus 5 apples is 7 apples. Hey, cool. So it's kind of weird. Isn't it weird that it's like more complicated than you'd think? So ultimately the product rule is if you have two things multiplied, you take the derivative of one times the second one left alone, plus the derivative of the second one times the first one left alone. I mean, if you're just to put it in common sense English, that's what it's really saying.
So is the du, the du times dv, is that just too small that we ignore it?
Yeah, ultimately it's going to get ignored because it's something really small times something really small. It's on its way to zero. But again, the thing that's annoying is everything in that expression is on its way to zero. Du is on its way to zero all by itself. It's just that du times dv is on its way to zero even faster. Again, it's the equivalent of saying, well, okay, I'm looking at my yard right now, and there's like a billion blades of grass. So then I go out there and I pluck one of them. I pluck a tiny amount of my yard. But then once that's done, I say, okay, well, I'm not done. I'm going to take now a tiny piece off of that blade of grass. Like you got nothing. You got no lawn left if you take a tiny piece of one blade of grass. And that's kind of the idea here. It's conceptually what's going on. That's not as formal of a, that's why it came from the 1800s version of calculus for dummies. That should bother you a little bit that I just kind of said, oh, this one's zero and that one is not. Like du times dv is zero, but du is not zero. Like that feels a little hand wavy, doesn't it? It feels a little like, how can you say that for sure?
So is it just to say it's not significant?
Yeah, I mean, in a sense, you could say it's really insignificant. I mean, that's kind of a good way to say it. So there's more proofy ways to kind of do this if you're interested in, and this is not what I just gave you is kind of a neat way to build it. As I said, I'm not going to ask you to do that on a test. This is not your book's way of introducing it. This is the simplest way I've ever seen to help somebody understand why it is the order that why you have to do what you need to do. Your book probably has a proof for it. What most books do, which is this terrible pedagogy, which is terrible learning style, is to just say, here it is. Here's the product rule on the very first part of the first page in a box, and it's all colored, and there's the product rule. And then they'll right below it say, then they'll prove it, as though you're like not believing them. I paid $200 for this book. I believe you. You're probably telling me the truth. So most of it's just skip right over the proof part. That's probably true. And then we just skip right to the problems. Okay, how do I get these problems right now? But I just like this better because we're making it, or at least getting some conceptual understanding of where this comes from. And also just because it occurs to me right now, your book is probably going to say it a little weirder than this. It's probably going to say something like, I'm not even going to look kind of on purpose, but your book probably says something like this. If you have y equals f of x times g of x, and that's not bad because they're telling you right there that those are functions of x. And it also, they look more like them than u's and v's do, right? Like you're used to seeing f of x equals x squared and g of x equals the sine of x. You're used to seeing that. And so then they would say something like maybe y prime is equal to f prime of x times g of x left alone plus f of x left alone times g prime of x or something like that. Do you see that as the same thing? But that's messy. It's got a lot of letters to it and so forth. That's one of the reasons I kind of like the version that I told you, where it's just u's and v's. It's so clean. It's so simple. But it's still the same thing, I guess. That's all I'm interested that you know. Okay, so let's try this out. So let's take this kind of slow. Let's see here. If I said, and we'll test this out to see if it kind of works. If I gave you the equation y equals, or I could say f of x equals whatever, and I say x, let's just say x times, not x squared times e to the x. You do not have a choice. If you want to go find y prime or f prime of x, you have no choice but to do the product rule because you have junk times junk. That's what you got to look for here is like, hey, I got junk times junk. Oh, I can't just use the power rule. I've got to use the product rule here. What do I do? So you get an answer to that. And then go one step further when you're finished with that and find, I don't know, f prime of -1. Like find the slope on that original curve at -1. And then we're just going to go cheat on the graphing calculator and see if that looks right. So let me ask you a question while you're sort of finishing that up. How do you decide which one of those is the U and which one is the V?
It doesn't matter, right?
Why not? You're correct.
Because you have to factor both anyways.
Yeah, notice you're multiplying them together anyway. And then once you're all finished, you're adding them, right? So it doesn't matter what order you multiply in. Isn't 3 times 5 the same as 5 times 3? That's the commutative property of multiplication. That's what mathematicians would call it. Doesn't matter what order you multiply in, so it doesn't make any difference. And addition's the same way, right? Isn't 2 plus 7 the same as 7 plus 2? Addition doesn't care. Now, subtraction does. 7 minus 2 is not the same as 2 minus 7. But because this is multiplication and addition, it actually doesn't make any difference. And for that reason, if I went back here, I could also say this is equal to u prime v plus uv prime. Like, does that make sense? I just wrote it. That's like 2 plus 7. I rewrote it as 7 plus 2. Like, it doesn't care what order it's in. And I point that out because when we move on to division, it's going to make a difference. But anyway, we'll get there when we get there. So let's see. You think you have an answer to this, and maybe you plugged in -1 for x, and so this is all code for. I'd sure like. That's sure a cool graph. I'm very excited about it. Could you tell us, or could you? I'd like to know what the slope of that curve is at -1. That's what this is all code for, right? Wow, what a fun looking graph. Look at all those cool curves. I wonder what the slope is at x is -1, and now you have a recipe for that. That's what the derivative is. And so what I want to do is just switch over to the graphing calculator real quick and like see, let's just kind of check and see if your answer is right. Let's see if this conforms to reality. So I'm going to stop this share for just a minute. And I'm going to share my other screen. I just took the time the other day to figure out how to get a graphing calculator on my screen. So you don't have to stare at that dorky camera that doesn't focus on my physical calculator. So let's graph this thing. So we're graphing y equals, and again, Desmos is way better. I'm just doing this because maybe you're sitting there with your test. I actually don't care on a test if you use Desmos or if you use your graphing calculator. But we can do this on the graphing calculator. So x squared times e is right there above the plus sign. So second e raised to the x. And so if I hit, remember last time I used this, the screen might be all screwed up. So it's a good place. Instead of hitting graph, it's a good idea to hit zoom. And then number 6 is standard. That kind of resets the screen to be 10 for the y max, 10 for the y minimum, 10 for the x max, and -10 for the x minimum. And so notice Desmos is better. That's like a black and white graph. It's all chunky looking, pixelated. It looks totally stupid. And I kind of need to see if I'm interested in that curve, which appears to kind of be flat and then it humps up and goes down and then goes back up again. I kind of need to see it a little better. And so you should know how to do this stuff, but just as a reminder, I can go to window and notice it kind of looks, the graph, if you will, looks interesting from about back here. I don't know, we'll call that -3 out to, I don't know, from 1 on, it doesn't look that interesting. So maybe I'll go -3 to 1 in the x direction. And then as far as height, maybe I'll go 2 up and -1 down. So I'm going to go to window. So for x minimum, I said I'm going to try -3, except for negative didn't pop out. I keep forgetting I can't hit my screen. This is so backwards to me. -3. There we go. And for x max, I said let's make it 1. Let's see, I can't. I can arrow. That's what I can do. For y minimum, I said let's make it -1, and for y max, I think I said 2. So now I'm going to get, if I hit graph, kind of a better look at the interesting part of this graph. Notice though, it's still colorless and totally pixelated looking. So now you should be able to kind of tell if your answer is right. Like you have an answer to f prime of -1, and now that you're looking at the graph, you should be able to say things like, hey, look, I'm looking at x is -1 right there, and I can clearly tell the slope is negative. So you better have got a negative. There's your first check. And then what kind of a negative number does that look? Does it look like more like -1 or -10 or -0.5? Like what roughly does that slope look like to you? Again, can you look at your answer and confirm that you got it right? Or perhaps now you're questioning that you blew it? And of course, I can cheat on the calculator and actually ask it that, right? I showed you how to do this before. Calculate button. So if I hit second calculate and I go down there to number 6, dy dx, that's code for slope. And of course it says, where do you want to go? And I say, I want to go to x is -1. And it says, there's your slope. So is that what you got? Like that's that kind of check. Did you get it right? Did you get the product rule correct? Because you had no other way to get that problem right. There's a multiplication going on, 2 terms that are multiplied. I can't get around it. So like on a test, like you should be able to write me a note. I love when people write cocky kinds of notes, like don't even grade it. I know this one's right, checked it. Or I know this is wrong because I checked it and the calculator says the slope should be about -0.37. And here's the calculus I did and I got 7.2. And so I know mine's wrong, but I just can't figure out why. I love that note because that shows in the real life you're not just going to go build the bridge based on your calculations. Your calculations won't work. The dangerous people are the ones that don't know that they don't know. If you know that you don't know, then you don't build the bridge yet. You wait and go ask someone else and check it a little longer, right? So it's kind of cool to be able to check your work. Before I leave this screen entirely, I want to show you something in my open math that was there before, but maybe you've never bothered to look, but it's time to look at this. So this is what you see in the student view. But here into course information, I pointed out before there's a couple of things in here. Well, this Calc 251 notes, time to print that off if you haven't printed it off. I fit everything you're going to learn in this class on 1 page. And so if you punch a hole in this and just have it handy or make 10 copies and give the other 9 away for Christmas presents. This is glorious. This is the result of hundreds of years of people just slaving away trying to figure this stuff out. How exciting would that be to open this up for all of your friends and family on Christmas morning? Just think about it. Well, notice here's what we've learned so far. Definition of a derivative. That should be like, oh, cool. Thanks for putting that on there. I'm going to ask you test questions that ask you about that. Power rule. If y equals x to the n, then y prime is n times x to the n minus 1. Product rule, just learned that. If y is equal to junk times junk, then what's y prime? U prime times v left alone plus u left alone times the derivative of v. And then I reminded you here, u and v are functions of x. Those aren't just letters. Those are random functions of x. And then notice on here is quotient rule and chain rule, and what's the derivative of trig functions, and what's the derivative of natural log, and like that's what we're going to do is go take the derivative of everything. And so in a sense, you already see what I'm going to be showing you for kind of the rest of this course. But you'll
I feel like
have
my eyes should.
Sorry, go ahead, Felix.
Oh, I was just saying, I feel like my eyes shouldn't be seeing this yet.
You're kind of right. That's kind of spoiling the fun.
Oh, where was on my open math again? I can't find it.
It is in course information. So class notes is where I'm posting every day. The notes that I'm writing for you in the lectures, and right above that, course information. And so, yeah, you're kind of right. As I said before, to Felix's point, this takes all the fun out of it. I mean, this is actually, if a person has time available and really enjoys math and isn't taking this just because they want to be a veterinarian and someone is making them, this is totally spoiling the fun. Like, to have time to figure this out yourself and so forth. So yeah, I mean, cover the rest of them up until later. Yeah, I'm letting you in on the secret, on the inner sanctum. Well, let's go see if that works out. Like, we just cheated on the calculator and we found out the slope is supposed to be negative 0.367. So let's see if this is, let's see how this works. Let's just do it real quick. And again, I'm assuming most of you probably got this right, but the derivative of this would be u prime. So the derivative of x squared is 2x times the v left alone plus the x left alone times the derivative of v. And again, e to the x is a little weird because it and its derivative are the same thing. And so I get that. Okay, cool. That's the answer I got. As far as I'm concerned, you're done. Is it kind of cool to be able to recognize that, hey, look, they both have an e to the x in them with a plus sign, and so the reverse of the distributive law would be to pull the e to the x out, and that would leave 2x plus x squared on the inside. And maybe that'll save me a little time when I go to try to figure out what f prime of -1 is. So that'd be e to the -1. 2 times -1 would be -2. -1 squared would be +1. And so that's kind of interesting. I just get -1 times e to the -1, or better written as -1 over e. Like, that's the nicest looking answer. Do you agree with that? Now, again, you should not be surprised if in my open math, if they ask you for an exact answer, because you can cheat to get every single answer in this class. If somebody just says, what's the slope at 2? You don't need calculus. Go push that dy dx button and you're done. Engineers will be pushing that button. All of you will be pushing that button if you ever need this in the real world. But mathematicians are really into perfection. And then also, 1 over e keeps you from cheating. I don't know about you, but a second ago when the calculator said the slope was -0.367, I didn't go, hey, isn't that 1 over e? Like, I didn't recognize that, neither did you. But if you bust your calculator out now and type 1 over e, you get the same answer, right? So it's like it's working. I know how to use the product rule, and it apparently works. It looked right on the graph. There's a physical reality behind this on the graph, and this math proved it or agreed with it. So, I ultimately like to say, it's like, I'm sorry that this is as complicated as it is. I wish it was just the derivative of junk times junk is derivative of junk times derivative of junk. But no, it's a little more complicated than that. Both cool and horrifying. Now we'll revisit this later in the term, because we don't know a lot of things yet. In other words, the interesting questions that would follow from this are things like, what if I said, I guess I'll say future here. Future questions that we'll answer will be things like, what's the derivative of x times the sine of x? Well, you don't know what the derivative of sine of x is. Well, yes, you do. You could go steal off that note I gave you. But like that's a product rule problem. Or, what about y equals x cubed times the natural log of x? I don't know what the derivative of natural log of x is, so I can't really do that yet. But it's like you got to kind of know the derivatives of all the other weird functions that exist out there to really practice this. Right now, the only thing is polynomials like x to the 7th and x to the 5th. You can take those derivatives because of power rule, and then e to the x. And so there's not a whole lot of problems you can be given right now. Does that make sense? So this will come up again, and it'll, our understanding of how to use it in all kinds of different circumstances will deepen. And you might even wonder, what about this? What about x times the natural log of x times the sine of x? Is there some kind of like a product rule for triples? Like now there's 3 things multiplied together. So is there some product rule for u times v times w? Like, or can you do this with what you already know? I mean, again, this is what mathematicians do. They just say derivatives are cool. Oh, okay, well, let's take the derivative of everything. So this class is now, if you will, devolving into that. We're no longer, all excited about finding the slope. We're just saying let's find the slope of everything. Interesting. So maybe just to do one more quickly, why don't you try this one really quick. Would you agree you could multiply that out if you wanted to? Because that's really x to the 7th times x to the 1/2. And since you add them, that'd be x to the 7.5 or x to the 15/2. And so its derivative then apparently would be 15/2 times x to what power? Can you do this?
13/2.
Yeah. 15/2 minus 1 would be 15/2 minus 2/2, which would be 13/2. Apparently, this is the right answer. But again, my question is, just for practice, like, can you get that right using the product rule? If you think of that as just x to the 7th times x to the 1/2, can you product rule your way to get the same exact answer? Just to kind of see if you got it. I'll give you a second and then I'll do it with you. If you have time, check it. So I would never use the product rule for this. It's too time consuming. I would do what we just did. Get rid of the product. But
Yeah, it looks completely different, and I'd have to do a lot of simplification to collapse it down, but I think it's the same answer.
yeah, it will be, but yeah, it's messy. There's a lot more steps. There's a lot more algebra to do. And so you don't do this. You wouldn't do this here. And you may have noticed you had an assignment that was like this before, and that's what they wanted you to do is multiply it all out. Because you can't do the power rule to that right now. So your 3.3 assignment had this question in it, or questions like this. If you can't get it to look the same, then you made a mistake, or your ability to simplify ugly algebra messes could use some improvement. take all of that stuff seriously and make sure your question gets answered before you're done here. Calculus is not hard, it's the algebra. All right, I'm gonna catch up. So I'm using what I wrote over here as my product rule. So it says take the derivative of u, that first one, so that'd be 7x to the 6th, times the second one left alone, then a plus sign, and then the first one left alone, it's the 7th times the derivative of the second one. The derivative of x to the 1/2. Bring the 1/2 down front, take x to the 1/2, subtract 1 from it. 1/2 minus 2/2 would be negative 1/2. And as Bale was hinting at, it's kind of like, oh, that can't be right. Doesn't that look not even close to 15/2? Like, you already know this is the right answer, right? It doesn't look anything like that. But don't quit too soon. X to the 6th times x to the 1/2. You add those. 6 plus 1/2 is 6 1/2, or 13/2. 6 plus 1/2, that'd be 12/2 plus 1/2, that'd be 13/2. 7 times 1 is 7, so it'd be x to the 13/2. And of course, I look at that and I think, hey, yeah, that's actually going the right direction. And then the same thing kind of happens again, which is I have 1/2 times 1, which is 1/2, and then 7 minus 1/2. 14/2 minus 1/2 would be 13/2 again, x to the 13/2. And now I have 7 plus 1/2, that's 7 1/2, that's 15/2. Oh my gosh, it's the same exact answer. And again, algebra, I still bet there's lots of you screwing this up. If you have 7 apples plus half an apple, don't you have 7 1/2 apples? Like, the description does not change of what you just have, what you have. So, sure enough, it's the same. So, don't do the product rule if you don't have to. But as I hinted at, most of the real problems of this course are problems where you're not going to be able to get rid of that multiplication sign. All right. Consider this question. This was also something that was in 3.3. Maybe I'll even write that down here. 3.3, we're told something like y equals, and I'll keep it simple just so it goes fast here, like x to the 4th plus 5x squared, but it was all over the top of, say, the square root of x. And in this case, notice there's a division sign. And back at the time, this did not maybe occur to you because I gave you some examples and we talked about it and so forth, but like, that division sign's a problem. Do you see that now? Like, multiplication was a problem, and so how much division is too, but you're able to get rid of it here, right? Like, you're able to get rid of that statement. In other words, you can say, since x is really x to the 1/2, you can say, well, that's really x to the 4th divided by x to the 1/2. And in that case, I'm subtracting exponents, so it'd be 4 minus 1/2, that's 3 1/2, or 7/2. So that's really the same thing as x to the 7/2. And then because of distributive law, these are both, because of the plus sign and distributive law, these are both divided by that. So then I'd have 2 minus 1/2, which is actually 1/2, which is 3/2. So I'd have 5x to the 3/2. And notice the division sign is gone, and it's just a plus sign. And so now, yeah, this works great for the power rule. So this was a power rule question for you back in 3.3 because you didn't have to live with the division sign. And so now you can say the derivative of this thing is apparently 7/2 times x to the 7/2 minus 1 would be 5/2. And then 3/2 times 5 would be 15/2, or 7/2. And then 3/2 minus 1 would be 1/2. And so this is definitely kind of the right answer. Because you're not stuck with the division sign, as you will be. You will be stuck with the division sign if I say, what's the derivative of x over e to the x? you're not going to be able to get rid of that division sign. And so it's like, you can already sort of predict that division must be complicated if multiplication was, right? And so if I say, let's try to do this without dividing. Again, I wish it was true that you could just say, well, the derivative of the top is 4x cubed, the derivative of 5x squared is 10x. There's the derivative of the top, done. Derivative of the bottom is 1/2 x to the negative 1/2. But you should understand from what we just saw that that's surely not going to work. I mean, I wish it did. But the derivative of junk times junk was complicated. So isn't the derivative of junk divided by junk going to be complicated? And maybe just to prove the point, because, you know, are these the same? Well, maybe they are. Well, let's keep going. 4 divided by 1/2 is 8. So 4 divided by 1/2 is 8. And then x to the third minus, notice you're subtracting 3 minus negative 1/2 is 3 plus 1/2. So that's 3.5 or 7/2. So you have 8x to the 7/2. Notice that's nowhere up here. There's no 8, there's no x to the 7/2. Like, this is not working. Not surprised, but it's not working. And so, you know, what do I have to do to deal with a quotient? What do I have to do when two things are divided by each other? How am I going to get the answer to this? And you can appreciate, as I said, it's probably a little messy. And so, again, let's go back to come up with a quotient rule. Let's go back to that same logic that we used before that I stole from Sylvanus P. Thompson. To build, not prove, but build the product rule. We started with y equals u times v. So what are we going to start with this time?
U divided by v.
Yeah, maybe u divided by v. And so before I even start, like, couldn't I do some algebra? Like, if I multiplied both sides by v, wouldn't I have that? And now it kind of looks like the product rule. Like, it's junk times junk equals junk. So, and then what did we say? What did we say kind of a derivative was? I don't know why I have to switch colors so much, but it's kind of like v gets a little bit bigger, y gets a little bit bigger, and u gets a little bit bigger. And don't forget what we're looking for. Since the original equation was y equals u over v, we're looking for dy dx still. That's still what we're trying to find. And so I'm looking at what I have down there thinking, I need dy dx. How do I get dy dx? Well, last time we divided by dx to get one because there's no dx's in this problem. But this is going to be similar. Well, let's just kind of proceed. So let's see, if I multiply v times y, I get v times y. If I multiply v times dy, I get v times dy. If I multiply y times dv, I get y times dv. If I multiply dv times dy, I get dv times dy. No such thing as math with letters. You got to just write down that you're going to do it, but there's nothing to do. You just write it down. So similar to last time, what kind of things can I do with this to make progress? You weigh in. What could I do?
Whichever one's going to 0, get rid of it.
Yeah, this thing, because it's a small amount of v times a small amount of y, that's going to 0 faster than everything else. What else can I do?
Replace anywhere where there's a normal y with u divided by v.
That's right. Back up here, I can replace y with u over v, or down here I can replace u with v times y or v times y with u. Like I can do that. Are any of those more helpful than any other ones? Vale's on the right track, but he didn't choose the most helpful option.
Could you do Vy, your first equation, and transfer that to U because Vy equals U, and then you subtract your U?
Exactly. In other words, can't this one be replaced with U? And then both sides have a U, so I can subtract the U off. Isn't that the same flavor that we did before? And so
Wait,
yeah, go ahead.
wait,
Yeah.
so you have in the middle you have V dy, and then you add y dv. Isn't that the same thing?
No, because it's V, which is some equation like the sine of X times a tiny amount of Y, and then it's Y times a tiny amount of V.
Oh, never mind.
So they're not quite the same. They're close, but they're not quite the same. And then just like last time, remember I'm after dy dx. And so now I think maybe I should do the same thing I did last time, which is divide everything by dx. And so now I have v times dy that gets divided by dx. And then plus sign, that means the next thing gets it too. So I have y times dv divided by dx. And then on the other side, I just have a du and it gets divided by dx. Except for this time now, because I'm solving for dy dx, I just kind of need to isolate this, right? I need that by itself, because that's what I'm trying to figure out here is what's dy divided by dx. So again, how's your algebra skills? What I'm really trying to do here is create a recipe for what did I do with junk divided by junk. So how's your algebra skills? Can you just stare at that and solve that for dy at dx? Is it intimidating for you to do that? You should see it as, well, the first thing I got to do is subtract all this junk from both sides. Subtract that. So now I'd have v times dy over dx equals du over dx minus y times dv over dx. And then I guess I would just divide by v. There. Now, staring at that, you should say that's, I don't know, I'm confused. Like I don't understand the directions that's giving me. Like that's kind of what you should be feeling right now. My guess is like, I don't know what to do with that. Like in a sense, I guess you could say this says, take the derivative of the top term. Remember u is the top one. It's this time it makes a difference which one is top and which one is bottom. Is 10 divided by 2 the same as 2 divided by 10? No, like we get a little more careful now. So use the top one. So it says take the derivative of the top one minus y, but y was like, what's y? Y was u over v. It's like, so that's really the u over v, and then times the derivative of the bottom and then divided by the bottom with no derivative. So it's like, wow, that's a really strange set of directions. And it kind of is. It doesn't feel very memorizable, very memorable. I'm not even sure I understand it. But there's some things you can do to make this look a little nicer algebraically. And this is what algebra is for. It's like supposed to make your life easier. So for instance, as I mentioned a second ago, really, I'm not really happy with having a y on the other side. I'd really like the other side to be just u's and v's, right? Like if those are functions of x over there, I'd really like those over there, and I don't really want this. And so if I replace this with what it's equal to, which is u over v, then at least over there, there is nothing. Well, and I think I'll even go one step further with this. Just because it's nice to write du dx, isn't this du dx really just u prime? Like it's a nicer way to write it. And then it's minus u over v times v prime divided by v, which doesn't really help, but still ugly. However, what I really don't like now is I don't like the fact that there's fractions over fractions. I have a u over v on the top as a fraction, but then it itself is over the top of v. And so I don't like fractions over fractions. Those are ugly and confusing. And this recipe looks, again, not very memorizable. But what's one thing I could do to that fraction to clean that up a lot? You algebra studs.
Divide the v across both terms.
Yeah, you can actually get rid of this v right here. And if you said out loud what that says, it says u divided by v. We did this in the previous section. This is kind of a takeoff of what Dominic said. Couldn't I multiply that by v up there? And as long as I did it, well, to the other side, either do it to both sides of the equal sign or do it to the top and the bottom. Because if I multiply by v over v, I really just multiplied by 1. Let's see if we can make this look nicer. We're multiplying by 1, so we're just making it look different. And so we're just wondering, will it look any better? Again, you should see distributive law, which means I got to multiply u prime is going to get multiplied by v. But then when it gets multiplied by this v, it's just going to cancel that out. So it'll be left with uv prime. And then on the bottom, you just have v times v. That is the most memorable. That's the most memorable version of the quotient rule right there. Like that, I could actually memorize. Let me rewrite the product rule quickly next to it. Y prime is equal to u prime v plus uv prime. I'm not a memorizer, I've told you. You have your note sheet already sitting in front of you. I just wrote the note that's sitting on that note sheet. But if you had to memorize this, do you see the similarities? Take a look at those two next to each other. This one says u prime v plus uv prime. What do you notice about the one that's up there? It's exactly the same. Except for division, there's a minus sign there. And for addition, there's a plus sign. And then, of course, the product rule has divided by v squared. And notice you're not taking its derivative. It's just whatever it is, square it. So if I had to memorize this, that might be the only shot I have at a form that would allow me to memorize it. It's like, well, they actually have something in common. But again, what is this really? It's a recipe. If I put it in English, this says take the derivative of the top function times the bottom one left alone, always a minus sign, top one times the derivative of the bottom one, and then divided by the bottom one squared. Isn't that a crazy set of directions? Like, wow, it's really surprising that it's that much trouble to take a derivative if something is divided. Like, man, I don't want to get too many of those problems. And so again, this is even worse. Like as a set of directions, this is worse than the product rule was. Related to, understandably, because multiply and divide are similar, but worse. So with our last few minutes here, let's revisit this question. Let's revisit this question back here. This was our original problem. And we know the right answer. And so could we follow that set of directions we just made for ourselves and actually produce that answer? Let's see if we can pull that off. But I'd just like to give you a minute to get ahead of me here a little bit. See if you can do that with the quotient rule. Understanding that this entire top function is the u, and this entire bottom function is the v.
Could we turn any quotient rule into a product? Like, couldn't we, I don't know if it's a dumb question, but like, couldn't we just put the x or the square root of x onto the top and then to the power of -1/2 and then do the product rule? Or does that not work?
That is a great question. Everybody understand that? That's worth considering. No, that's not a dumb question at all. That's a fantastic question. In other words, what Martin is saying is, couldn't I rewrite this as x to the 4th plus 5x squared, but then just take x to the -1/2 and move it up to the top. I'm sorry, x to the +1/2 on the bottom, move it to the top as x to the -1/2. Now it's junk times junk, and I could use the product rule. That's a great question. The answer is yeah, you can. And part of the reason you even said that is because you're thinking the product rule is nicer. And so, yeah, that's an awesome question. It's not always that easy. Like if there was a sign down there, like how do you move sign to the top? It'd be like sign to the -1 power. There's like sometimes what you move up can be ugly. Or what if it was natural log of x down there and you moved it to the top? Now it's actual log of x to the -1 power. And so it feels like, oh, I don't know what to do with that. So that's an awesome question. Nobody thought to ask that in the previous period.
So for this problem, is v root x, or is it 1 over root x for doing the problem?
It is root x. In other words, the v is x to the 1/2 power. I'm gonna give you another minute and I'll catch up. All right, I'm going to catch up. So by way of the quotient rule, what would the derivative of this be? Well, again, I'm just taking these a chunk at a time up here. And I'm going to purposely switch to a different color and just note that I'm doing it. So the quotient rule says u prime. Well, u was the top. So the derivative of the top is 4x to the 3rd plus 10x. That's the u prime times v left alone. V is that square root of x. So times square root of x. Now, because I'm going to have to simplify this later, I'm going to write it as x to the 1/2, but that's my v. So there's the first part. Then it's always a minus sign, not a plus sign like it was for the product rule. Always a minus sign, done. Then it's u left alone. U was x to the 4th plus 5x squared. And then it's times, so there's our u. And then it's times v prime, the derivative of v. Well, v is x to the 1/2, so its derivative would be 1/2 x to the -1/2, thanks to the power rule. So there is a gigantic disaster that represents the top, the numerator of that, and then divided by v squared. No derivatives, just whatever v is, the square root of x, then square it, which is particularly nice in this case, right? If you're square rooting something squared, cool, that's just x. So that's particularly nice here. Now again, you're done. Calculus is now done. That's the right answer. Ugly, messy, and so forth. You should be cleaning this up some. For most questions on tests, I'm not just going to ask you what's y prime. I'll say now find y prime of 2 or something. But plugging 2 into that would be hard. I probably am not even going to succeed with a calculator plugging x of 2 into that. So, can you clean it up a little bit? Can you make that a little less messy? All kinds of simple things you could do wrong here. Like, do you notice distributive law? Even if you don't bother to write it, that parenthesis is extremely important because x to the 1/2 is getting multiplied by both of those terms. So I'd have 4 and then x to the 3rd times x to the 1/2. I'm adding exponents. So that'd be 6/2 plus 1/2. So that'd be 7/2. And then 10 times x to the 1/2. X to the 1 times x to the 1/2. I'm adding them. 2/2 plus 1/2 is 3/2. So there's that. Then I'm subtracting, and then same thing happens. I got to take 1/2 times both terms, distributive law. So 1/2 times 1, since there's a 1 in front of x to the 4th is a 1. I'm sorry, 1/2. 1/2 times 1 is 1/2. And then x to the negative 1/2 times x to the 4th. Again, you're adding those. So you have 4 plus negative 1/2. That's 3.5. Or 8/2 minus 1/2 is 7/2. And then it's 1/2 times 5, which is 5/2. And then x to the negative 1/2 times x to the positive 2. So that's 4/2 minus 1/2, which is 3/2. What dumb math mistake am I making here? Again, this is a rare moment where I'm making it on purpose. It's just a dumb algebra mistake.
Weren't you supposed to multiply the exponents, not add them?
No, because they're being added. In other words, you have x to the 3rd times x to the 7th. You add in that case and get x to the 10th. If you have x to the 3rd to the 7th, then it's x to the 21st.
Yeah, we get those backwards.
I did that right.
You distribute the negative
Yeah.
through that.
Isn't this
term.
minus all of this junk?
Yeah.
Yeah.
That's a minus sign. Like, there's just a lot of stuff. That's the kind of thing on a test. I'll just tell you right now how I'm going to grade this. If this is your test, I'm going to circle that and say something like, dude. I'm going to tease you a little bit. And when you look at your test, I hope you find yourself going, oh yeah, I need that. And I'm not going to take off very many points for that. But work on that stuff. Like, this is not simple. Like, you really got to be able to speak the language of algebra. The other thing I say a lot is Shazam, like a miracle just happened there. Now, of course, this is really good news because notice there's some stuff to collect together. So if I have 4 apples and I take 1/2 of an apple away, then I have 3.5 apples, which is 7/2 of whatever that thing is. And then kind of tried to lose that minus sign. And then I have 10x to the 3/2 minus 2.5 of them, or 20/2 minus 5/2 would be 15/2. 10 is dying. And then the description doesn't change. And so that's a nice clean answer. Look at that. That's the same. No, it's not. It's not the same answer. I don't know why right now. I just assumed to be the same, that I wouldn't make any dumb math mistakes.
Did you forget the -1? Like 7/2 is -1?
It's all still divided by x. You have to factor that out.
Oh, yeah, we're not done. Thank you. This is still divided by x, right? So for a second there, I thought I was wrong. So how do you divide by x? Well, don't you subtract? In other words, isn't x to the 1st x to the 2/2? So that's the same as x to the 2/2. So then if I go x to the 7/2 minus x to the 2/2, isn't that, my pen is dying. I'm gonna plug it in. Oh, I'm gonna have to let it die. Can't bring it back. Do you see that it's the same? It actually is the same answer. So I'm going to end up with 7. I'll fix this after I charge the pen before I post it. But can you see that it is going to be 7 halves x to the 5 halves and then 15 halves x to the 1 half? And so indeed it is going to be the same. So as I said before, like that's a pain. Like, don't do this problem with the quotient rule. I mean, if you're left to your own devices, if you can see that you can actually divide those, then divide them, because it was a lot more trouble to get the same exact answer in this way. But the point is like quotient rule is a thing. Like it really is this complicated. It really is that, if you will, nasty set of directions right there that it takes to kind of pull this off. It's just kind of surprising, cool, terrifying, fun, awful.
I have a question. So when you were rewriting that whole thing, in the green area, you've got a backup there. You've got 4x cubed plus 10x times x to the 1 half. Why isn't that x to the negative 1 half?
Because according to the description, that says u prime times v, like not the derivative of it, just it.
Okay.
You with me?
Yeah, well, I think so. I'm just kind of confused because you've got the square root of x in the denominator, which I thought would be like 1 over x to the 1 half, because your exponent would be negative.
No, it's down there as a square root. So therefore it's down there as x to the 1 half. Now, if you chose to move it to the top, it would become x to the negative 1 half. But just because it is on the bottom doesn't mean it's automatically negative.
Yeah.
It's negative
Okay,
when you switch it. If it's up, it's on top and you move it down, then it goes to negative.
I see now. Thank
So it
you.
is positive. I love it. Great question. Make sense of this. Get to the bottom of it. So we'll practice this a bit tomorrow, but you haven't practiced enough to probably feel good about this yet, but you know enough to do a whole bunch of the 3.4 assignment now. Feel free to wade into that, and maybe you show up tomorrow with some specific questions. But we'll probably take 20 more minutes tomorrow and just dink around with product rule and quotient rule, and answer a few questions. But again, my open math is really cool because it gives you 3 tries, and so you can look at my note sheet, so you have the product rule and quotient rule written down in front of you, or write them down yourself, whatever. But then test it out, put your answer in. If it doesn't work, then but what I'm worried about, and is going to happen, I'm just telling you to expect this, is a lot of the time your mistakes are not going to be the calculus part, it's going to be the algebra part, because there's just so many exponent rules that are going on here that are just hard to keep straight, and distributive laws everywhere staring at you, and it's just so easy to mix something up. And
Doug, are there any telltale signs of what rule to use?
basically you should just go back to say, what am I looking at? Am I looking at junk? This isn't a good place to look at it. Am I looking at junk divided by junk? Because you're right, you're now seeing the future here, which is I now have 3 rules to choose from. I have the power rule, the quotient rule, and the product rule. And so, what am I looking at here? If I'm looking at junk divided by junk, then I should be thinking quotient rule. If I'm looking at junk times junk, if I'm looking at junk times junk, then I should be thinking product rule. That's really all you got right now. If I don't have any things multiplied or divided, then I'm thinking, oh, at least for what right now, I'm thinking, oh, just regular old power rule, whatever the exponent that thing is. If there's not things multiplied or divided, then good, that's a pain. So you're right, that's a big part of the kind of the future of this class is ultimately, if I just give you some random problem out there in the world, it's kind of like, geez, do I use?
Yeah, you don't want to go down the wrong road and just like end up with some ridiculous answer, spend half an hour trying to do a problem that's not going to finish.
Well, unfortunately, there's really only one more rule, and that's something on your note sheet called the chain rule. So there's really 4. Fortunately, there's not 18 of them. Then there's all the individual things, though, like what's the derivative of sine? That's not a rule. That's like something you have to know. And we got to discover that, just like we discovered the power rule happening. And again, you should sort of feel like we're a long ways away from f of x plus h minus f of x over h as h goes to 0. We're now into the shortcuts of all this kind of stuff. I mean, can you imagine taking that last problem that we did right there and putting in x plus h for x everywhere, and then saying, okay, now let's proceed. Like, if you're suffering with quotient rule, you're missing the point. Like, you should be going, yay, the quotient rule. That is so awesome that there's a shortcut for this. Otherwise, this would be impossible, because this problem has square roots to get rid of and fractions. Remember how we had a way to get rid of fractions and a way to get rid of square roots? This problem's got both of them. Wouldn't that be fun? And power rule. So, ooh, so these shortcuts are really cool. Just don't forget that we're kind of a long ways away from just finding the slope in kind of an obvious way. All right, get yourself out of here. Stay after if you have questions. I'm gonna charge my pen up right now in case I need to write.
So for the thing that we got assigned yesterday, do we just have to like contact our groups kind of outside the class or whatever?
Yeah, if you made enough of a relationship during that time to share each other's phone numbers and you guys get together kind of on your own to work on it, whenever you want to work on it, text each other or whatever, that's certainly awesome. In the end, as long as you, however you go about that, got something to me in a week, then awesome. You can certainly stay after today and ask me questions too.
Gotcha.
See you tomorrow.
Sounds good. See you, Cheyenne. Sounds like everybody's good. All right. See you tomorrow, Julissa.